Hello, this is Group 1 presentation. My name is Medhat. We will be presenting Chapter 4 from the book Verification, Validation and Testing of Engineered Systems by Angel. The chapter is called System Verification, Validation, Testing Methods, Non-Testing. Parts covered will be prepare verification, validation and testing products. Part 2, perform VVT activities, and Part 3, participate in review. Application of all that will be on our group project entitled Concession Stand System in Movie Theater. First section will be requirements verification matrix. For the structure of the matrix, it will have the following: the ID code, requirements traceability, verification methods, stages, and verification procedure ID code. Verification methods are analysis, inspection, demonstration, testing, and certification. First verification method is verification by analysis. It's used when other methods are not possible, cannot be done, and not feasible. It's based on mathematical models, simulations, algorithms, calculations, charts, and so on. The second is verification by inspection. It's used when intent is to show compliance with a very simple requirement. For example, weight, size, shape, or color. It's used when it consists of non-destructive examination, and typically in component and subsystems at the production phase. The next method is verification by demonstration. It is similar to testing method, except it is a safer approach. It's used when intent is to watch a system accomplishing certain undertaking. The best example given in the book is by Charles Lindbergh demonstrating a solo non-stop flight from New York to Paris in 1927. The next method is verification by testing, and this method should be considered the default choice for each entry in the verification matrix. Next method is verification by certification. It may be acceptable instead of a test on verified article. Such certification should indicate the standard procedure used when test was conducted. It's used when a new system is a variant of an existing system already tested and proven, when full verification cycle is expensive and time-consuming, and in component and subsystem manufacturing setting. Applying the verification methods to Group 1 project, which method are we going to use? Testing is the principal method. The verification by certification is not needed and will not be used. The verification by demonstration is not recommended. The analysis will be used, and inspection is the easiest and should be used. Next section is System Integration Laboratory, SIL. It is used to solve the problem of finding faults only at integration system components and subsystems. One of the approaches used is creating a testing environment. SIL description, it consists of the following: equipment and facility necessary to operate SIL, simulations of the system necessary to operate system in real time, monitoring and testing equipment, and facility to finalize performance tests. There is also the distributed SIL. It's for very large systems dispersed over a large geographical area. It must be tested concurrently. A distributed system integration laboratory is used. In addition, there is the generic SIL. In large organizations are advised to build SIL facility. Now, for applying the SIL concepts to Group 1 project, what methods to use? Taking into consideration that the nature of the project is being limited and small, in addition, it's central and not dispersed over several geographical areas, then SIL may be used for testing. Generic SIL does not apply, and the distributed SIL does not apply. Next is the hierarchical VVT optimization. Its goal is to improve the VVT plans for the whole system, subsystems, and components. It uses iterative process so as to eliminate redundant VVT activities, adopting less costly VVT methods. It may be used when requirements have been defined and system has been decomposed into subsystems and components. Advantages of hierarchical VVT approach are redundancy is reduced, cost is reduced, it's easy to implement, and it fosters comprehensive visibility. At the end, when we apply those ideas on our Group 1 project, hierarchical VVT optimization is recommended to be used. That's the end of my part, and I leave the next for my colleague Laura.
Defect management and tracking. The VVT team is often tasked with detection of system defect management and tracking. There is a drive for increased system quality to keep track of problems and defects. Implementing a system to list and prioritize defects to be fixed is needed. Defect tracking logs help identifying the amount of work that is involved, understanding the fault, locating it, and fixing the defect. This task was mainly conducted by software developers, but it has been extrapolated and modified to be engineered system domain. Identifying causes of operational failures and defects in products and services is different in each organization and may be categorized by using back risk factors (BRF) tables, such as Table 4.1. BRS provides information about the relative strengths and weaknesses of organizations. Adequately controlling these BRFs will minimize the risk of business disturbance such as financial losses and diminished reputation. Like in Table 4.1, it depicts a list of BRFs associated with an organization engaged in developing and manufacturing large, complex engineered systems, which in the categories we have design hardware, maintenance, housekeeping, and more, and it has a description of the back risk factors. More about this is the defect management and tracking. This aims to analyze fault history in order to determine the organization's BRFs as well as develop an organization individual risk profile. These identify general weaknesses of an organization in order to improve key development parameters that may improve the organization's quality. This defined a new strategy to better manage fault and risk, and it helps in defining acceptable quality standards of manufacturing equipment based on equipment histories, frequency of component failures, etc. It helps on maintaining quality problems during the entire product lifetime, that is through like the development, production, use, maintenance, and disposal phases. Defect classification. Before starting to do anything and to manage and track any system quality metric, a company or a project team should define goals. These directly affect the specific data that are tracked and the complementary analysis effort. With these goals in mind, the team or company can determine the exact data to be collected. For example, the goal of defect tracking could determine the cause of origin of defects in order to improve the development process. Sometimes classifying defects is difficult and may result in ambiguous, overlapping, or incomplete categories. But still, the classification of defects into categories can help seeing important insights because it enables to improve the system development and maintaining process. For example, in figure 4.8, this depicts defects categorization scheme tailored for systems. In this figure, defects are first categorized by the origin, that is the phase in which the defect was introduced. The defect was introduced into the system, and depending on the phase, each defect is assigned a type, that is the area within a particular origin that is responsible for the defect as shown in the middle layer of the diagram. All defects, regardless of origin, are further classified based on the defect mode, that is a designator of why the defect occurred. For example, a defect which was introduced during the design phase where a user input had been omitted could be classified under missing. An integration phase defect where a system implementation was incorrect will be classified under wrong. Often defects are assigned various attributes. For example, in table 4.2, this describes the typical defect severity attributes and on table 4.3, this describes the typical defect priority attributes. In general, defects should be worked on in a severity order. When a critical or major error occurs, other PBT activities may be suspended until the defects causing the error have been corrected or a suitable workaround has been identified. In addition, information may be collected or computed as part of the defect management and tracking processes. For example, the number of defects, defect discovery rate, defect closure rate, effort to close defect, and the elapsed time to close a defect. Now, defect management and tracking. While not all defects can be avoided, it is possible to minimize the number and impact that they have on a project. One way is to implement a defect management process that focuses on either preventing or identifying defects as early in the process as possible. The defects management process should be based on the following general principles. The process should be risk driven, that is, basically, strategies, priorities, and resources should be based on the extent to which risk can be reduced. And secondly, the process should implement defect measurement as an integral part of the development process and be used by the project team to improve the process. The primary reason for gathering defect information is to improve development process when a defect or failure has been detected. A well-designed activity workflow should be followed, like in figure 4.9 depicts such defect management and tracking process. To achieve goals, developed teams involved should examine the types of defects that occur most frequently, as well as the number and types of defects that occur in each subsystem and component. These latter measures help the BBT team identify system elements that require extra testing or major modifications. In addition, development teams should examine the phases in which defects are encountered. These data gathered could be plotted to identify defect trends. Defect analysis, therefore, should be focused on the circumstances leading to the introduction as well as the nature of discovered defects. The intent of using the information is usually to characterize or analyze the environment or a specific development process and then to improve process in order to eliminate the cause of defects. Like many suppliers of systems or components have made defect tracking a part of their ongoing procedure.
The section Requirement Testability and Quality evaluates multiple concepts to aid in the creation of requirements. To begin with, let's dive into evaluating requirements for testability. Using our projects as template, concession stand system in movie theater, let us recall and evaluate some of these. For repairability, if we take the requirement, the system shall be designed and optimized to ensure efficient and rapid processing, maintaining waiting time for customers within a maximum threshold of 15 minutes. This considers both normal and abnormal conditions, which might be at peak hours or in the contrary, low attendance. For the stability, we have requirement the system shall detect any food shortage to fulfill the daily demand and have a course of action by making a requisition to supplier. In this requirement, we laid out the action which will change the state of the system, it being going into shortage of inventory. This will be resolved with the requisition to the supplier, which creates stability. For simplicity, we have requirement the system shall offer visual information to communicate the offers and prices. This is a language that can be understood by diverse groups. It does not require an elaboration into the topic. Now let's go into the requirements quality by attributes. Understandable being one of them, we can find one of our requirements. There shall be a reserve fund for unexpected costs. Can be easily understood by all stakeholders involved, regardless of their area of expertise. The second quality attribute for requirements to review is precise. Looking at requirement, the system shall maintain operational availability within the specified time window from 11 a.m. to 12:30 a.m. daily to align with the cinema's opening hours. So this requirement not only is precise with the system, it also aligns with the operability of other systems involved, which is a plus. For feasibility, the requirement, the system shall implement a comprehensive food preparation area management process to ensure that all food preparation areas are consistently clean, well maintained, and compliant with hygiene and sanitation standards. This is a feasible requirement that goes hand in hand with training and preparation, required to all staff, which must be a norm. There are multiple known ways to obtain this requirement. The section Another way to evaluate requirements is by syntactic and semantic means. One tool that provides indicators to evaluate on requirements are as follows, and some of these include optionality. If we have stated a requirement, the system shall have an emergency alarm as stated by the Metropolitan Fire Service safety guidelines if possible, we would be missing an essential and important part of rules and regulations that might place individuals at risk. This being a must, places the system at risk of being shut down from operating. Another indicator is weakness. Evaluating a requirement, the system shall have an appropriate space for the client to wait to be attended, meeting standard of ADA inspections. And change it to the system may have an appropriate space for the client to wait to be attended, meeting standard of ADA inspections. We can analyze the fragility of the statement. At last, we evaluate subjectivity. For example, the system shall have the capability to provide quality products to the customer that meet or surpass quality criteria to satisfy expectations and requirements. If we add the word better and state, the system shall have the capability to provide better quality products to the customer that meet or surpass quality criteria to satisfy expectations and requirements, then we would have a subjective requirement that falls short of the normal requirement description and turns this into an opinion.
Hi, this is Anuvia Puga from Group 1, and I will be presenting on section 4.3.5, failure mode effect analysis. So in this section, we see that failure mode effect analysis, short for FMEA, consists of a bottom-up process to identify failure modes within the system, which in return allows to determine how to eradicate potential problems. The main purpose of FMEA is to be proactive in mitigating failures and measuring how impactful the consequences are and the frequency in which they may occur. In doing so, they can implement the priority of what to look at and what can be removed and what can be left in the implementation of the system. So, and it is done in sections, which we'll review on the next slide. As mentioned in the previous slide, the failure mode effect analysis is implemented during the design and manufacturing of a system. So the terminology used in this failure mode analysis are failure cause, which identifies underlying causes when we create a process to fail. So it could be in the design cycle of it, or parts or manufacturing, where something can be backtracked to see why the result is not being achieved. In failure mode, the creation of how a system or a process may fail is looked at, which reviews the way a system is being used and the result of the failure in it. In failure effect, they identify the immediate results in the failure in a function or functionality. And failure severity finds the consequences of a failure mode by identifying what the worst outcome of that type of failure by degree of injury or property or system damage, which can also be applied to environment, or in the case of self-driving cars, if it's going to affect humans or the surroundings. And this is something that could be applied to one of the projects where they're using UAVs to do deliveries for groceries, in which is something that is mentioned in their project, which is path planning and having the UAV travel without any issues as far as it crashing into a building or not finding the correct address. So this is something that I think could apply to something as such as that project. The basic types of FMEAs mentioned in Chapter 4 are design FMEA. This process is implemented during the design phase of a system. So this allows to determine how failure modes affect the system operation. Functional FMEA analyzes potential problems and loss of functionality, the estimation of the probability of the problem, and the potential damage to expedite and implement solutions to the issue. System FEMA analyzes the system more in detail, looking at each component of the system to understand how a failure will affect individual parts and its interactions. So as opposed to the functional FMEA, the system FMEA looks at each component and how they talk to each other, or their interaction, to see how each part will be affected, which in return goes back to the functional FMEA, which looks at the structure in itself, not so much how the relationship with each element or component. In the process FMEA, the procedure that is mainly implemented on manufacturing processes, so processes that identifies limitations of resources or equipment, tooling, gauges, operator training, or other sources of errors. So this could be, as it mentions, operator training, human error, limitations of resources, again, budget costs, which it all goes full circle. If there's errors that are not identified on time and there's no solutions identified on time, and how it's the priority that is given, then the time that the solutions or the project will not be met in the timeline that was initially given. So this last process looks at other things other than just a functional or systematic part of it, but also it could be said that it's more like budget or human error. And these processes related into my group project, which is a concession stand, it goes in hand with using the software and the computers to understand what the customers are looking for and to find a way to reduce time in waiting for a product, or to reduce time in waiting in an area, and in return the business will create more profit off of that. So these could be implemented in the sense that to analyze what is causing a system or a section of the concession stand to take longer to take orders, or why are they not being given on time, or is there issues with the food that is provided to the business, and again, they could be applied to the project that has a UAV flying the groceries, which I thought was very interesting, because I know that there's companies that have already done that, but in making it faster, there's also other implications that I think these processes would probably be well applied to. This concludes my section. Thank you.
So to continue on with the presentation, first of all, let me introduce myself. My name is Dana Zamorano. So now that we have talked about testability and quality, I would like to talk to you a little bit about a way that we can achieve these requirements, which is done by model-based testing. First of all, we need to understand what a model is and why it is important. A model will allow us to predict and understand the system's behavior, and this is actually very cost beneficial for companies, as we can do try and error, and it will not affect in any part a physical process or even the material that we are using. It uses a variety of modeling paradigms, which can be different types of languages, different types of simulation softwares, or different type of requirements introduced into the system, or different types of complexity analyzed within a system. And it actually analyzes accuracy, quality, and possible behaviors of outcomes of the systems. As we know, most of the times we don't have constants within our systems. For example, maybe when we're trying to simulate supply chain planning, you will not have the same demand daily. So it allows you to interact with those type of different behaviors within the system, and it allows you to obtain the different types of outcomes that you will receive depending on which characteristics you input.
And to prove if a model is actually being done correctly or not, you can use a model checking theory, which first of all, the steps to follow is that you first need to choose a model checking tool. As I previously mentioned, there are many type of models that you can use, such as softwares, maybe a 3D printing, and so on. So you first of all have to identify which one is most beneficial for you. Then you actually create the model system, and then you have to create the formal specifications of the system. This is one of the most important parts whenever you're trying to create a simulation or a model itself, as you do need to understand what the requirements are, and you have to be able to specify the the outcome that you want to obtain. As if you do not provide the formal specifications to the system, you will not have one accurate one that would allow you to actually present it to the real life situations. The next step would be to activate the model checking tool, and it will allow you to understand if maybe you need to do some debugging if your model is working as intended, or what is going on with your model if it needs any type of modification. With the results obtained, you can do your analysis, and then you can move on to decide if your model is optimal for implementation or if it needs to have some changes. Whenever you implement your model and the outcome does not come in the real life as it does in the outcome, we have something called a conformance failure. As we know, a model is not out the real system, so when you implement it, it might not be accurate in the real life situation. So the actual result versus the expected one will have discrepancies. This can be caused due to a system failure, or a modeling error, or a specification error. As I previously mentioned, if you don't have your specifications correctly, this is one of the facts that could happen. We could have a conformance failure. So now that we have talked about the process of how to do the model checking, we can talk about what can it be used for. Within systems, we can have finite state machine systems, and this will allow you to have the coverage for the strategies. When we're talking about a finite state system, it is one that follows a sequential logic, or in other words, it can execute a type of flow to be able to come to the outcome. So this type of modeling will allow you to cover the strategies as to how to perform that flow of the process and be able to provide the results. Additionally, it allows you to verify system requirements or designs, and it allows you to obtain the final outcome. As we know, whenever we're working with designs and maybe we're trying to choose which material is the best option or the most resistant one, you can use this model checking to analyze if maybe the properties of the material are the accurate ones for the outcome that you're expecting. Or maybe if you, for example, want something to be resistant but lightweighted, you can change the requirements, play a little bit around with the material, and using the model checking, you can compare the last result to the results you're expecting to obtain. And that way you can do those comparisons and changes. And finally, I would like to talk to you a little bit about why model-based testing has its benefits and its weaknesses. Some of the benefits are that it provides proof of correctness, so it will actually allow you to analyze if maybe your process, your systems, or your requirements are correct. It can allow you to test early in the system's development phases. So a lot of times whenever we're implementing a new process or a new system, a new design, a new product, you need to start working with what you have, and maybe you don't have the material on hand. You can do this type of modeling, and will actually save you a lot of cost expenses, as you can do the try and error without a problem. And lastly, as previously mentioned, it's very cost beneficial for the companies to do model-based testing prior to implementing the real system. Some of the weaknesses are regarding the state explosion. As we know, some systems can be really, really complex, as they may have many interactive components, and maybe when you're trying to model, you do not have the capability to compare all those requirements. So you're trying to make something really, really abstract and try to simplify it, and during that simplification, you can maybe leave out some types of requirements. Also, it has its mathematical limitations depending on the software. Sometimes it is not compatible with certain mathematical critiques. It is also non-trivial, This means that it requires experts to understand the requirements in the technology that is being used. If you're not familiar with the requirements you're trying to implement, you will not be able to actually do the modeling. Maybe you can be great at modeling or using the software, but it is really important for you to understand what you're trying to do, what the requirements mean, and what outcome you're expecting. And finally, it is not the real system. Even if your model is 100% working as you intended, when you try to implement it to the real life, it can always vary, and it can always present maybe outcomes that you were not expecting. But maybe one solution that could be provided is that whenever you're implementing and you see something not running as the simulation was doing, you can always go ahead and implement that new problem to the simulation and maybe come out with a new outcome.
Participate in reviews. This section is divided into 3 categories: formal technical reviews, expert team reviews, and group evaluation and decision. We'll see a little bit about each category on the following slides. Expert team reviews is a phrase used as a generic term which includes inspection, walkthroughs, audits, and peer reviews. Inspection is characterized by examining documents as well as collecting various metrics about the inspection process itself. There are 2 types of inspection. It's document inspection and system inspection. Document inspection is a discipline engineering practice for detecting defects in technical documentation and preventing the consequences on their inaccuracies from leaking into production or actual use. And system inspections are a formal process of verifying the condition of existing systems and infrastructures, such as electrical equipment, automobiles, houses, aircraft, among others. In walkthroughs, the creator of the evaluated object presents it to a group, and they in turn analyze it sequentially and helpfully recognize errors, coding bugs, or potential performance problems. Audits use sampling of actual process performance to determine if an organization is actually following prescribed practices or the practices they claim to be following. And lastly, peer reviews. These are made by people that are normally not the managers of the person whose work it's gonna be reviewed, nor the full-time checkers or inspectors. The primary idea of this is to achieve an open and honest reviews by, among other things, protecting the responsible engineer from being threatened. Formal technical reviews are used to evaluate the quality of a system at various points throughout its life cycle. The role of this is to bring together the most relevant people to criticize the work done, solve open issues, and decide the action plan that the team requires to follow in order to pass the next formal review. The typical technical reviews and audits are listed in the table shown. We have, for example, system requirement review and the critical design review, just to mention some. The generic process for the formal technical review are step 1, management preparation, 2, planning review, 3, overview and review of procedures, 4, individual preparation, 5, conducting review, 6, rework follow-up, and 7, exit evaluation. About the formal technical review activities, we have some that are done before the review, some are done during the review, and some others are done after the review. For example, we have pre-review activities that are collect results of activities, prepare material for review, analyze the material, and create a review package. During the review, we have reviewing the agenda, reviewing the project and system status, reviewing technical issues, open issues, and the action list, and take the decision, pass or fail the review. And lastly, we have the post-review activities that may be like creating minutes on the review, recording decisions and agreement, reach along with a list of follow-up actions items, and review the final report. Group evaluation reviews. It's attended by technical experts reunited specifically to evaluate engineer systems and make a decision regarding the suitability of the system to meet relevant requirements. According to the lecturer, there is more effectiveness of groups as decision makers than to individual members. More ideas are generated and there's more informational resources. The risk of this are shared information bias, cognitive limitations, group polarization, groupthink, and social lofting. The decision methods may take different approaches, like they may follow informal approach as brainstorming and formal approach by consensus agreement or parliamentary procedure, and quantitative approach by modeling group decision making. Thank you.
That will be all from our part. We hope you enjoyed our presentation. This is our references. And if you have any questions or doubt, you can reach out to us at any moment. Thank you.